Okay, so the next section is about relating those rotational and translational motions. Okay, translational motion is also called linear motion, and sometimes I call rotational motion as angular motion. They are the same as well. So the equations for translational motion have many similarities to those for rigid body rotation. As it turns out, there are direct relations between the two, and we already talked about one of them. Okay, so we're considering the object is rotating about radius r. You can see r here. So this is the rotation axis. It's very important every time you're solving those, look at the rotation axis first so that you can define your r, because that's the distance from the rotation axis to the point of either the point on your rigid body or the object rotating from that rotation axis. And this v is the tangential velocity. That means this v, the line of the v or the vector v is perpendicular to the line along r. Okay, so this is 90 degrees here. And this arrow here shows the angular velocity. Again, you can see that this is counterclockwise. If you remember, we use CCW for counterclockwise. You can also say that it's coming out of the page or positive z direction, right? We remember the right-hand rule. So try to see all those things that now we had the pieces. Now we're gonna put them, starting to put them together. Okay. So r is constant, first of all, so the radius is not changing, and v is tangent to the circle, so we call this tangential velocity, linear velocity. And omega is the radians swept out per time, because it's theta over t, right? And v is the distance covered with time, distance covered per time, because it's like x over time, or in this case like s over t, right? And if r changes, v changes. Okay, so if you make r to 0, what happens to v? 0, right? So r and v will change in the same ratio, and we will talk about it in the equation. Okay, so first of all, let's start with the distance. Okay, we're going to relate the distances as I just showed in the previous video. We use the definition of arc length. So the relation between the distance traveled and the angle of rotation is s equals to r theta. S is the arc length here. You can see it on the figure. R is the radius for the rotation part. And theta is how far you go, okay, in angular form. And again, theta is in radians. Okay, it's very important. Now, if you take the derivative of the both sides, because this is how you relate the distances, what about the velocities? Take the derivative. Left side becomes ds over dt. Right side, you're taking a derivative of this function, r theta, but r is constant, so it comes out of the derivative. It becomes r d theta over dt. And what is d theta over dt? It is omega, right? And ds over dt is v. So you're getting a new equation, which is v is equal to r omega. Okay, and this is how we relate translational speed v to the rotational speed omega. Again, the key is again r, the radius. Okay. So these are the two equations, and now we have both the linear and the rotational stuff in the same equation. So that's why we call those relations between angular and linear motions. Okay, and for the definition, we're going to look into the period this time, and the definition of the period is defined as the time required for one complete revolution. And we've done this in chapter 4, actually chapter 6, when we talked about centripetal force, so uniform circular motion, right? So you already know this. So the period is a time, but it is a special time. Okay, it's for one cycle. So you know that time is equal to distance over speed, right? And we know that the distance is one cycle, so we're going to say, and we have that later on, but 2 pi r is the distance for one cycle. And speed is the linear speed, so we're going to start from there using those equations. And then we know that v can be written in terms of omega using v is equal to omega r, right? This was the relation we just got. And then what you see is r's are going to go away, and then period is simply 2 pi over omega. Okay, so you have a little bit more simplified version. So the angular velocity is also related to period, and it doesn't change with r. You can see that t is equal to 2 pi over omega. There is no longer that r affects this equation. Okay, we have related angular and linear velocity, so we use that. And now we are going to get the acceleration as well. So we do the same thing. We have this relation v is equal to r omega, and then take the derivative on both sides with respect to time. Left side becomes dv over dt, right side becomes d r omega over dt, but r comes out, so it becomes r times d omega over dt. The reason r comes out because r is constant, right? And then what is d omega over dt? It is alpha, and dv over dt is acceleration. We are going to specifically, we need to, because we will have more than one acceleration, a linear acceleration, we need to realize that dv over dt is tangential acceleration because it comes from the tangential velocity. Okay, so we're going to label this a as at, you can see it here, and that t is the tangential acceleration. Okay, we will also have radial acceleration, as we will talk about it soon. So, and I never memorized this. I think about where it came from. Okay, this a comes from dv over dt, and that's related to tangential velocity. V is tangential velocity. So that's why the acceleration should be tangential acceleration as well. Okay. And you can kind of see it in this figure that was where v is, and that's now at, and because they point the same direction in this case. But of course it depends on if it's speeding up or slowing down, right? They might be opposite as well. So this is a slight twist, as we will also have another acceleration component, so that's why this we are putting the subscript t, okay, and that's going to be a very important thing later on. There's usually like students confused about there, so make sure to understand where it came from. Now we put those together, this equation becomes at is equal to r alpha. So this tangential acceleration can be written in terms of angular acceleration in terms of r alpha. Okay. Again, it's important to note that acceleration is tangent to the path. So tangent means it's going to be perpendicular to r, the line of r, right? And if omega is constant, so think about this. If velocity is constant, acceleration is 0, right? So if angular velocity is constant, then angular acceleration is 0. And then tangential acceleration should be 0. Why is that? Because of this equation. Okay, alpha is 0, then at is 0. Simple as that. So as an example, consider someone sitting on a stool placed on a merry-go-round. If the merry-go-round increases its angular velocity, the person will tend to tip over backwards on the stool. If the merry-go-round has an angular deceleration, the person will tend to tip forward. Regardless, and even if the angular velocity is constant, the person still feel an acceleration toward the center, right? That's the centripetal acceleration, and we are going to call that radial acceleration. And remember that magnitude of that, v squared over r. That means a rotating object can experience two acceleration components, a tangential one and a radial one. The radial one is our centripetal acceleration. Okay, so but we are putting r as the radial. So it's like tangential and radial, those are the letters we are keeping, and this is the tangential acceleration, and that is the one if you have a change in omega, because then there is alpha. So if this alpha is 0, then this tangential acceleration is going to be 0, and that would be a uniform circular motion, right? If the object rotates at constant angular velocity, then alpha is 0 and at is 0, as we just said it. This is the special case we looked at earlier, right? And this is what we have. And in that case, the only acceleration is the radial component, which is the centripetal force, centripetal acceleration, and it is v squared over r. But if you have both those two components, then we need to understand how to find out the total acceleration. Okay, now we're noting that, again, the equation we got, v is equal to r omega. That's the tangential velocity related to the angular velocity using the radius r. And we can also write radial acceleration in terms of r omega square, right? How do we get there? We have that v squared over r. So I'm going to show that quickly here. AR is v squared over r. What is v? V is r omega. Square that, divide by r, you get r squared omega squared over r. One of the r's are going to go away. You get r omega squared. And that's what you have as a radial acceleration. So you can also write the radial acceleration in pure angular momentum, angular velocity way. Okay, so it's like it's given here in the v squared over r. It's linear velocity, but it also depends on omega as well. You can see it from this equation. So again, if we have both of those components, so we have the velocity here, the tangential velocity change that creates an angular acceleration. Then you have that acceleration, tangential acceleration, okay, along this tangential velocity direction. Again, it could be the same direction or opposite. If they will be the same direction, if it is speeding up, they will be opposite. AT and V are going to be opposite if it is slowing down. And the radial acceleration is always towards the center because it's called centripetal acceleration, center seeking, if you recall that. If you have those two, then since those two are perpendicular to each other, you can use Pythagorean theorem to find the total acceleration here, right? And that's what we're gonna do later. But so I'm gonna write it here. That A can be written in terms of these AT and AR are kind of components, AR squared plus AT squared. Okay, so then you can find out what the total acceleration is. So if they're just asking in the problems, if they're asking you just find the acceleration, that means they're asking you to find the total acceleration because they didn't specify if it was radial acceleration or tangential acceleration. If you have both of them, if only one of them are non-zero, then of course total acceleration will be that. But make the details are very important. How you label them, how you what are the names of those. So we need to get used to those. Okay, I'm gonna solve the example in the next video.